Post it later. Okay, and we're set. Okay, so today we're starting at the very front of our textbook with section 1.1, and we're going to talk about sets today. Sets are a very simple idea, but a very important idea because a lot of mathematics is built on top of it. So the very simple definition is here. A set is simply a collection of objects. Okay, so what does this mean? Well, a set could look something like this. We have a very simple kind of set. And if everyone could double check that your microphone is muted, I would really appreciate it. Someone's is open. Let's see if I can figure it out.
Professor, I can barely read that scene of yours. You got it on. Can you make it to where yours is the only one we can see?
Yes, that's how it was a second ago. I was just trying to see if I could figure out whose microphone was on.
It's either Eric or Luan.
What? Okay, so
your mics are open.
Can you see my screen as a full screen, Nick?
And no, it's still
okay.
Gallery.
So there's a few ways that you can change it. If you click in the upper right of the Zoom menu, the Zoom window, you should
I got it now.
View, and that should work. If you want to make sure it doesn't change at any point, you can hover over my screen and click the 3 dots and then pin video. And I think that should.
Thank you, it worked.
Okay, good. Okay, so back to sets. This is a very simple set with 3 numbers in it, 1, 2, and 3. And I want to point out a few things. You should notice that I used these curly braces around my set. And in mathematics, this is what we're going to use for sets. And then inside of the curly braces, I've listed out the elements. Okay, so that's sets in a nutshell. But there's more to talk about, because we're going to spend, I think, the whole lecture today getting into some of the nuances. So this is the first little nuance here. The order of the elements in your set doesn't actually matter, because a set is just a collection of objects. It doesn't matter what order you put them in, it's still the same collection. So if I take this set, 3, 2, 1, it has exactly the same elements as this first set that we talked about a minute ago. So it's actually the same set, even though the elements are written in a different order. And it also doesn't matter if we duplicate items in our list, because if you write down the name of an item more than once, you still only have, that single item, like this. Maybe I have 1, 2, 2, 3, 2, 1, 3. So I've listed 1 here and then here, but 1 is still in my set, if I list it twice, it doesn't change the fact that 1 is in the set. And the same for 2. It's been listed 1, 2, 3 times, but that just still tells me 2 is in the set. And same for 3. So it's still just a set with 1, 2, and 3 in it. Okay, so this method of writing sets, zoom out a little bit here. This method of writing sets by listing out the elements can get tedious pretty quick. Even for this set where I've listed out 1, 2, 3, 4, 5, 6, 7 elements, you don't want to write that out all the time. And a set could have thousands of things in it. It could even have an infinite number of things in it. So we need some other method that we can use when we have those larger sets. And that's something called set builder notation. And I can just write down an example and then explain to you what it means. So we have X, and then I put a vertical bar, and then I'm going to write.
Professor, can you zoom back out? I needed to get the rest of the top part.
Sure, we can go back.
Thank
Is that far
you.
enough?
Perfect.
Okay. Okay, so I'm going to finish writing this out. So we have our curly braces, we have an X, a vertical bar, and then I'm going to write a short little equation. X squared minus 1 equals 0. So the first thing I'm going to do is tell you how to read this set. So what does it translate to in English? So the curly braces tell you that it's a set. So this is the set. This letter X tells you the letter to use for the elements. So it's the set of X. The vertical bar means such that. And then you continue reading. In this case, there's a formula. Let me make a little note here that the vertical bar means such that. Okay, so when we just write out the elements of a set, it should be totally clear what elements are in it. But if we use this kind of notation, the set builder notation, there might be a little bit of extra work to figure out what actually is in this set. So let's take a moment to just work that out. So the sentence tells us that it's going to be numbers, x, that satisfy this equation, x squared minus 1 equals 0. So if we want to figure out what elements are in the set, we have to solve that equation.
Professor, could you zoom back out? I still hadn't finished getting the rest of that previous top you just finished. Right? Yeah, there.
Okay. So maybe I'll just wait a second so that you can.
Thank you.
And then just let me know when you're finished so I can move
We'll
on.
let you know.
Okay.
All right. You can scroll down to as far as notation. I got the rest.
Okay. Okay, so let's continue solving. Practice a little bit of our algebra skills. So x squared minus 1, that's what's called a difference of squares. We have x squared minus 1, and 1 is the same as 1 squared. And if you think back to maybe your last algebra class, you probably learned how to factor differences of squares. And you take the first number x, you add the second number 1, and then you multiply by the first number x minus the second number 1. So this one is fairly straightforward to factor as long as you remember that. And then now that it's factored, we know that one of these two has to be equal to 0. So x plus 1 equals 0, or x minus 1 equals 0. From this first equation, we can tell that x must be equal to minus 1. Or from the second equation, we can tell that x has to be positive 1. So those are the two elements in this particular set. Any questions so far?
I have a question.
Yes, go ahead.
In the equation up at the top, it's x minus 1 equals 0.
Right.
But then when you came down and solved it, it's now x minus 1, x squared minus 1 squared. Where did that minus 1 squared come from?
Okay. So just think for a second about what 1 squared is. What is 1 times 1?
It's still 1. Is it just a
Right.
way of simplifying how you think about it for the next part? Okay.
Right. Because
Okay.
I want to think about this as a difference of squares. That's why I wrote the square there. Okay, so I told you a second ago that the set builder notation is a good way to write large sets. And this set that we worked through only had 2 elements. So before we move on, let me add another example here at the end of how you can use it to define maybe an infinite set, a set with an infinite number of things. Okay, so we'll start the same way, the set of x such that, and now I'm going to write a little statement. X is an even integer. So this statement, or this set builder notation, is a little bit different than that one. There I had an equation, but I can also use statements like this to build sets. So this set contains numbers like 0, 2, 4, 6, and like -2, -4, -6, and so on and so forth. So there's actually an infinite number of things in this set. And using set builder notation, I'm able to define it in this shorthand way without writing out the alphabet. And it sounds like someone's microphone is open again. So please double check. Okay, thank you. Okay. So is anyone still writing, or does anyone have questions before I go to the next?
I'm good. I'm caught up.
Thank you. Okay, so in the sets that I've talked about so far, all of the things inside of the set were numbers. But actually, sets can contain any kind of object, not just numbers. So, for example, I could have the letters A, B, C. And I can also have more than one kind of thing in a set. So I could have letters and numbers, like this. And, well, I could have anything else, too. For example, I could throw in the state of Oklahoma. Okay. So this is a perfectly good set. Probably not one that you'll run across in the real world, but if you wanted to make this set, you could. And for my second example here, there's a tricky thing about sets. A set can actually have another set inside of it as an element. So this set could have the number 1, but it could also have the set containing 1 as an element. So remember, this is a number and this is a set. So they're actually different things. And we can put both of them in the same set. And you can put other sets too, like maybe this one. Three, 4, and 5, or a set with 3, 4, and 5 in it. And there was a good question in the last class, so I'm going to go ahead and answer it in case you don't think of it. There was a question about whether this set, the set containing the number 1, is different from this set. So it's a set with a set inside of it, with 1. So what do you think? Are these the same or different?
I'm going to go out on a limb here and say the same.
Okay. So they're actually different sets. So the reason in a nutshell is that this first set has a number inside of it, right?
Theo sao học rồi?
Can you repeat that? Can you repeat your question?
Lớp 4 trời 4 rưỡi. Rồi xong lớp 4 giờ.
Yeah, I can't tell who's speaking. Still can't really tell. Please make
Wong just showed up.
Okay, so maybe his mic was open when he joined. Okay, so just make sure your mic is muted. Okay, so back to this little example. The thing to remember here is that 1 is a number. So this set on the left side has a number 1 in it. This other set has a set inside of it. So this set has a set as an element. This set has a number as an element. So that means their elements are different, which is why they're not the same set. And I know that's tricky. That's why I wanted to make sure I mentioned it in class. Okay, so there are certain sets in any math class that you're going to deal with quite a bit. And they actually have some special symbols that we use for shorthand. So I want to take a moment to tell you about them. The first one is the set of integers. So these are the whole numbers like -2, 0, 53, etc. And the symbol for the integers is this. So it's a z, but instead of the normal single connecting line between the two horizontal bars, we have a double line. So like I said, these are the whole numbers. I can list out a few of them. We have negative numbers, 0, and then the positive numbers. And you could continue counting positive numbers forever, and you could also continue counting negative numbers forever. That's why I put these little dots here. The rational numbers are the fractions. So they're the numbers that you can get by dividing numbers from the integers. And the symbol for the rational numbers is a Q, a capital Q, but I've put an extra vertical bar here. Just as a reminder, I can write a few examples of rational numbers. So like a half. 3 is also a rational number because it's equal to 3 over 1. And the same goes for any whole number. Whole numbers are also rational. And maybe we can do a negative example, -7 over 15. And you could list lots more rational numbers. There's an infinite number of those as well, just like the integers. And finally, we come to the real numbers. And the symbol for these is an R with an extra vertical line. The real numbers include special numbers like pi that you learn in geometry. You might have run across the number e before. That's a real number. You also have things like the square root of 2 and -42. -42 is a perfectly good real number. 0. And I'm sure you can think of lots more numbers because as long as your number doesn't have an imaginary I in it, it's going to be a real number. Okay. So I left the complex numbers off of my list because we aren't going to have much opportunity to talk about them in this class. But if you're interested in the complex numbers, they also have their own symbol. And it's a C with a line through it. And the complex numbers include the square root of -1, which is better known in most circumstances as the number I. And it also includes all of these other numbers. So any real number is in here. You can have 3 minus 2i. You could have 5 halves. Okay, but you should all already be familiar, at least to some extent, with all of those sets. The next idea I want to talk about is the concept of cardinality. And this is, well, it's a fancy word for the number of elements in a set. So for example, we can go back to the first set that we talked about today and look at its cardinality. And, well, we just have to count. There are 1, 2, 3 elements in this set. And something to notice is that I've given my set a name. I've said capital X is equal to the set with 1, 2, and 3 inside of it. So the reason is that I want to introduce this shorthand notation. So most of the time we want to write a set using a letter like this one instead of writing out all of the elements in a set every time, just to save ourselves some writing and time. And the cardinality also has a shorthand. You put vertical bars around your set. So if I put vertical bars around X, it means the number of elements in the set X. Like so. So it's just 3. And you've probably seen this kind of notation before, the vertical bars written around something. So it could be an absolute value, which tells you about the magnitude of a number. You might have also seen it when you've talked about length. And these ideas are all related to each other because they're about the sizes of things. And when we want to think about the size of a set, we're going to talk about the number of elements in it. So not a length or a magnitude, the number of elements. The next idea is another one of those tricky ones. It's also possible for the number of elements in a set to be infinite. So there's an idea of infinite cardinality. For example, the set of integers. The set of integers is infinite, right? You could count forever and never finish counting through all the numbers. That's what infinite really means. And in the case of the integers, there's actually a special symbol for its cardinality. And it's a, see if I can get it correct. It's a Greek, excuse me, it's a Hebrew letter, not Greek. And I drew it poorly. But it's called an Aleph null. So in this particular class, we're not going to have much opportunity to talk about infinite cardinalities. It's actually an extraordinarily complex subject because there's actually different sizes of infinity. Just to name an example, the integers, like I'm talking about here, have a smaller size of infinity than the real numbers. But if you want to really delve into the reasons why that's true, it gets pretty complicated. And that'll have to be left for another math course that you might take in the future. Or if you want to maybe look it up online somewhere, sizes of infinity, you could explore it yourself. Okay, any questions before we move along? Okay, I guess everyone must be good for the moment. So in this first section, we're going to learn lots of new terminology and symbols, and that continues on this next page. So the next thing I need to talk about is the shorthand notation for saying that an element is in a set. So if lowercase x is in the set capital X, then we'll use the shorthand notation little x, and then this symbol is in X. So this symbol is something like a C with an extra line in it. And it roughly translates into English as X is an element of. And a lot of the time, you might want to say X is not an element of your set. And in that case, you take your symbol, that means is an element, and you just draw a line through it to mean that that is not true, essentially. So X is not an element of X, is what this would be.
How would we draw that symbol? I can't exactly make it out.
Okay, yeah, it's kind of small in the notes. So you would want to draw something like a C and then put an extra little line through it. So it looks a little like an E, but not exactly.
Thank you.
Okay, so let's just look at a quick example. The letter B is an element of the set with A, B, C in it. And the set containing B is not an element of the set with A, B, and C. Okay. So this set has the letter B, but it doesn't have the set containing B. You're still writing, so I'll pause for a second. Okay, so let's move along. I've talked about this idea of when two sets are the same a little bit already, but I want to make sure we have it written down what exactly it means when two sets are equal. And, well, it's kind of obvious. Two sets are the same. They're equal if they have the same elements. And just like we use the equal sign with numbers, we're also going to use the equal sign with sets. So this idea of two sets having the same elements breaks down into two conditions. If an element is in X, then that means it also has to be an element of Y. So looking at this little expression here. So that's one of my two conditions. So if lowercase x is an element of the set X, then it also has to be an element of the set Y. And something I should point out, so using lowercase letters for the elements of a capital letter set is something that you're going to run across a lot in mathematics. So make sure you pay attention to whether you're looking at a lowercase letter or an uppercase letter. Uppercase usually means a set, lowercase usually means an element. So going back to this expression, it also works the opposite way. If lowercase y is an element on this side, then it also has to be an element over there, if they're the same. And that's the other condition. If lowercase y is an element of the set Y, then it's also an element of the set X. So sometimes you're going to see later on in the course that it's useful to think of this equation as two separate things. So you're kind of taking a single idea and you're breaking it down into two simpler ideas. And sometimes that comes in handy, as we'll see as the semester goes on. Okay. And we can talk about a couple examples here. This first one we've kind of already seen. I have a set with the numbers 1, 2, and 3 in it, and it's the same as this other set with 3, 2, 3, and 1 in it. And that's because all the elements that appear over here are also in this list, and all the elements in this list also appear over here. So the order doesn't matter. It doesn't matter if you write something more than once. And I'll do another example with some set builder notation. Now I have the set of x such that x squared plus 3x plus 2 is equal to 0. And this is actually the same as this other set with two elements, -2 and -1. And this gives us another opportunity to practice our algebra skills. In order to check that this is true, we have to make sure that the numbers satisfying this equation are actually -2 and -1. So let's come down here and see if we can factor this out. Spend a couple minutes on this. So this is what we want to end up with. We need to fill in two numbers, And if you think back to your algebra class, we know that these two numbers need to multiply together to give 2 and add together to give 3. Does anyone know what the two numbers are? Any ideas? Yes, 1 and 2. So 1 times 2 is 2. 1 plus 2 is 3. So that's what works. And this tells us the two answers to the equation need to be where x plus 1 is equal to 0 or x plus 2 is equal to 0. And that means this first one means x should be minus 1. And the second one tells us that x equals minus 2. So after we work through a little bit of algebra, we can see that the numbers that satisfy this equation in the set builder notation are actually these two numbers in the other set. Any questions so far? Okay, so mostly what we've discussed is the relationship between sets and the elements that are in a set so far. In this next little section, I want to start talking a little bit more about the relationships between more than one set. So in this case, I'm starting with two sets, x and y. And here, I'm trying to tell you what a subset is. And this means that if every element of the first set, x, is an element of y, then x is a subset of y. And then there's a little bit of notation. And let me go ahead and write down an example. Sometimes it's a little bit hard to process these definitions when they're written out in words. And a simple example helps clear them up. So this is the kind of thing I mean. So this first set has the two elements A and C. This other set has the first four letters of the alphabet, A, B, C, and D. And all the elements over here, both of them, appear in this other set. And that's what I mean by this first set is a subset of the second one. All of the elements of this one are contained in this other one. We can also have relationships between the bigger sets that we've seen today. So for example, the integers, the whole numbers, are a subset of the rational numbers, the fractions. And we also know that rational numbers, fractions, are all real numbers. So that means the rational numbers are a subset of the real numbers. Okay. And you can see that this kind of notation, so instead of saying the integers, I've replaced it with a symbol, and the rational numbers have their own symbol, and then we have this other one for subset. So a whole sentence is made into just a few little symbols. And that's really the reason why we need to learn these. If you don't want to write paragraphs and paragraphs out in English, you need to know this shorthand. Okay. And then one more example, going to use a little bit of set builder notation again. And this is the set of x such that 3x squared minus x minus 2 is equal to 0. And this is not a subset of the integer. And in order to represent that not a subset, I take the regular subset symbol and draw a slash through it. And this is a common theme, well, in most walks of life and in math too. If you draw a slash through something, it means not that, okay? So if you see a symbol that you know with a line through it, it means not what that symbol is. Okay. And I'm going to leave this as a little bit of an exercise for you to figure out on your own why this set is not a subset of the integers. So what I want you to do is try your hand at factoring this, or maybe using the quadratic equation or something similar to that. So you can get a little bit of algebra practice. So just find the solutions to this equation, and you should see why that is true. Any questions before I move on? So there's a unique and fairly important set, and it's the set with nothing in it. It's the set with no elements. And we call it the empty set for obvious reasons. And there's a few ways to write it. This is the first way. So I just have a set using curly brackets, and, well, nothing is inside of it, so it's empty. And there's another, probably more common way that the empty set is written in mathematics, and it's a circle or a zero with a slash through it. So there's an idea that's closely related to subsets, and this is the idea of a proper subset. If X is a subset of Y, but isn't actually equal to Y, then it's what's called a proper subset. And the notation for this is very similar to the subset notation, but instead of putting a line underneath, we just leave off that line. And let me scroll up a little bit so I can remind you. This is the notation for a subset. So it's this C shape with a line underneath. Well, I guess it's usually more like a sideways U if you see it printed in a math book. So a proper subset, we just leave that off. And here's an easy example. The set with the first two letters of the alphabet is a proper subset of this set with the first, let's say, 4 letters of the alphabet. So each element, A and B, also appears over here, but there's some extra elements on this side. So that means this one cannot be equal to that. A useful analogy to these symbols, the way that you can help keep them straight, is their relationship to the less than and the less than and equal to or equal to sign. So you might remember that this one means strictly less than, and this other symbol means that there's a possibility that the two numbers could be equal. So like 1 is less than 3, but 3 is less than or equal to 3. And this line is very similar to the role that our line plays with subsets and proper subsets. So this is like, it could be equal to, that's what that means. And for the proper subset, this means that they are not equal. Any questions before we move on?
What's an example of a subset that's not a proper subset? I'm not sure I fully understand the difference.
Yeah. So the easiest way would just be to keep these two sets. So A, B, C, D is a subset of A, B, C, D. And the reason for that is that all the elements over here on the left side are also over here. So A, B, C, and D, but they're equal to each other.
So just a normal subset is always going to be, like a non-proper subset is going to be equal.
Yes. So if you know exactly what the elements of a set are, then you could always write it that way. But maybe you have some sets, a couple sets, and you're not really sure exactly how they're related to each other. Maybe they're kind of complicated. And in that case, you might want to use this symbol just to say, oh, there's a possibility that they might actually be the same.
Okay, I see.
And when we get to making proofs, so proving mathematical statements, we're going to see some cases where we want to use the subset symbol because we might be trying to prove that two sets are equal to each other. But that's for a little bit later. Okay, so moving on to
Professor, what was the line on the arrow pointing down to under that last example? Oh, hang on, I need to get that.
okay. And I was just pointing out the relationship between subset and proper subset and strictly less than and less than or equal to.
So those aren't needed at all, I'm taking it?
No, I guess not
Okay.
right.
All right, never mind.
Already, but. Okay, so now we've come to the idea of a power set. And it's a fairly simple idea to write down. The power set of a set X is the set of all subsets of that set. And there's this notation for it. We have P for power, and then we put the set inside of parentheses. So this is written something like a function. So you might be used to seeing something like f of x. This is a different function, p, for power. So let's think through, for a small set, what the power set looks like. We'll do one with just 3 elements in it, the letters A, B, and C. Oops. So the power set of X is a set of all of the subsets of this set. So what subsets can you make out of these 3 elements?
A and B.
Sure, so we can have just A and B together. Anyone else feel free to say a few more.
B and C.
Good. Can you think of another set with 2 elements inside of it?
A and C.
The A and C.
Right, A and C together. What other?
A, B, and C still be included in there
Yeah.
as a subset.
Right, the whole set is also a subset because all of the elements are contained. Good.
That's confusing.
It is confusing, I agree, the first few times that you see it, and then you just kind of get used to the idea. Can anyone else think of other subsets? There's a few more that we've missed.
The
BA.
individual elements.
A, B, and C individually.
Okay, so we've had 3 answers. I think the first one was B and A together, but remember that if you change the order of elements in a set, it doesn't actually change the set itself, and we already have a set with A and B. So adding B and A together wouldn't add another set because they're the
So
same.
what if the set just contained A, just B, and just C?
And I think that's what the other 2 answers were. We can have sets with single elements in them. And there's 3 of those. Are there any more subsets? Oh, and someone typed out that. Those single sets. So there is actually one more set. One more subset of
The
X.
one with nothing in it.
That's exactly right. The empty set is also contained in this set. It's also a subset, excuse me. So the reason is that, well, there's nothing in here, and nothing is contained in something. Sort of a strange way to think. But if you're wanting to see if all the elements in the empty set are contained in here, there's nothing to check because this doesn't have anything in it. Okay, so how many elements, how many subsets do we have?
Eight.
There's 8. Good. And the reason why I'm asking is that there's an important relationship between the number of elements in a set and then the number of subsets. And let me just go ahead and tell you what that is. So if the cardinality of my set is equal to n, so that means I have n elements in my set, then the number of elements in the power set of x, and the shorthand notation for that would be a power set with the vertical lines around it for cardinality. That's going to be equal to 2 to the n power. So this is a useful little thing to keep in mind if you're trying to write out all the subsets of some other set. Then this tells you how many that you should have, and it helps you double check that you actually found all of them. So if you have a set with 2 elements, then you have 2 squared subsets. If you have a set with, let's say, 10 elements, then there's going to be 2 to the 10 power. That's 1,024 subsets. Okay, so you probably don't want to try doing that by hand, but if you did, that's how many you would get. And this also points to the reason why this is called a power set. So you probably wondered, why would you ever call a set of subsets a power set? And this relationship is why. It's because the number of subsets is an exponent. It's 2 to a power. Okay, so any questions about power sets? No? Okay, so we have, it looks like 4 minutes left in class, which isn't quite enough time to move on to the next topic. So this will be our stopping point for today. So if there aren't any more questions, we can go ahead and stop there. But before you leave, let me go ahead and mention something. I've posted your homework for this section already. Let me show you where to find it. If you start the course homepage on Blackboard, you'll see an assignments button on the left side, and then you can just click through to find your assignment for section 1.1. And the instructions are here at the top. And it already has, I think this is the correct due date since I'll be wrapping up this section on Friday. And the instructions are here. These are the exercises from the textbook that you're going to need to complete. And they're on these pages, 12 to 13. And as you work through the problems on your own paper, or you're going to work through the problems on your own paper. And then,
Professor, we don't have you Friday.
oh, sorry, I was thinking of my other class. So I'm going to finish this section on Monday. That means this due date is going to be moved back another class period to the following Monday. But that's the only change. It'll still be the same problems. And you might want to go ahead and get started on them because we've covered quite a bit of the material already. And when you're done with them, you're going to take a picture, and you can take that with your camera, like your phone camera, or you can—
Or we could scan it on a scanner in our printer.
Right, if you actually have a scanner, or if you use one of the scanners on campus, yeah, you can do it that way. And then once you have that file, you'll hit this button here, Browse My Computer, to find that file on your computer and upload it using this Submit button down here. So are there any questions here at the end of class?
Not really.
Okay, so I will see you next Wednesday, and we'll finish up this section and then maybe move on to the next one.
good weekend, Professor.
Thank you. You too, Nick.
Hello, Professor.
Hello. Did you have a question?
Yeah, I think I just missed writing on the one at the like, if S is the subset of the Y, but it doesn't equal to Y, then it's equal the proper subset of Y notation. I think I'm missing that one. So can you go back and I take a picture of that one real quick?
Sure. Let's see which page.
Yeah, I think this one.
Is this the example that you were missing?
Yeah. Uh-huh.
Okay.
All right. Can you go a little bit more? Yeah. All right. I got it. So thank you.
You're welcome.
Thank you. Have a good weekend. Bye bye.
You too.